तो क्विज जो है ना आपकी आखिरी उसमें होगा 10 मिनट्स में और उसी में आपकी अटेंडेंस होगी। अच्छा जो स्टार्ट हुआ है अभी
स्टार्ट है।
So let's recap the two types of friction we studied so far. One was called, can you give me the name, the first one? Static.
Friction mechanics.
And the other was? Now, I don't know if I have told this before, but you know, to organize these different concepts in your mind, you need a strategy where you put things in relationship to each other. So it's not enough just to know what is static friction and what is kinetic friction. You should know how they are related, yeah, how they are different and how they are similar, so that they combined can be compared to something else, right? So you know the difference between them, yeah. One is like during the motion, and the other is to prevent motion, right? But there is one thing which is common between them, right? And that is they both are tangent to the surface. So if you have a surface, actually two surfaces trying to move, yeah, or moving or trying to move, whatever the case is. So the force which you call friction, whether it's static friction or kinetic friction, it will always be parallel to the surface. And in this sense, they are different to the normal force, because normal force is perpendicular to the surface. That is one thing. And you also need to know their common name. There is a common name. What will be your name for this? If I ask you one name for both. No, friction, there are other types of frictions coming up. You know, the reason I mentioned this thing is because this rolling friction is totally different. So it means that rolling friction now is a third type, which is different from both. So there are names which you may not find in the book, but you will find elsewhere. Yeah? One is called dry. It's called dry friction. I mean, this looks like dry friction, but it's not. It's just a terminology. People don't call it dry friction. Okay. The other name which you will find, and I like that that name the most, and it's called Coulomb friction. What is the spelling of Coulomb? C-O-L? Yeah, Coulomb friction. Because the mechanism behind these two is Coulomb friction. You know, those atomic forces, right? Interestingly, rolling friction is not Coulomb friction. So all the theory I explained, like there are those atomic bonds, yeah, and when you try to stretch them or you compress them, so this is also Coulomb friction, and so the Coulomb forces are behind this friction, but they're also behind the normal force, right? Of course, that's not a friction force. So, but in rolling friction, the mechanism is not those bonds and breaking of bonds, and it is an entirely different mechanism, and it is not in the scope of this course to explain it. But I'll just give you two brief hints, okay? The reason you have rolling friction is not those bonds and breaking, but because this thing, which you call the wheel, right? It has rubber, right? So it can be deformed. So it is not as, I mean, although you can still model it as a particle for other problems, but as far as understanding this phenomena is concerned, it is stupid to think of it as a single body. So there are actually multiple parts, and they are internally movable relative to each other. Yeah? So that complex phenomena can only be understood in a course called fluid mechanics. You must have heard this name. Fluid mechanics, hydraulics. It is something which the civil engineers and the mechanical engineers, they study, right? So it is very unlikely that you will have that course in this curriculum, right? But you know the whole thing. It is the reason why I'm not going to get into that detail. But one thing which we must know, that rolling friction is a consequence of fluid mechanics, because the tire makes the wheel a non-rigid body, and this makes it a different kind of friction. So it has its own name. It's called rolling friction. And the criteria to call it rolling is that there must not be any slippage. So have you seen sometimes, I mean, those who actually, those who drive wildly, they have this skidding thing, yeah? So if there is any slippage between the tire and the road, then you will never call it rolling friction. It will be then kinetic friction. So if you are if you are driving normally, all the friction you can have is the rolling friction. So it means that the kinetic friction is zero and the static friction is also zero during that time. That's all you need to know about rolling friction. So, but the mathematics is still the same. The maximum friction is still dictated by that coefficient of, so we learned this thing as well. Small f is typically the symbol we use for friction, whether it's static friction or whether it's kinetics. We will also use the small f for rolling friction, R for rolling. So if you want to have an equation for this, so it will be of the same form, mu times the normal force, right? And this will be rolling friction. Similarly for Fk you have mu k and the normal force. And for Fs, mu s. Can I have an equal sign there? Here we can have an equal sign. I can't have an equal sign there. Because this expression, mu s times m, is the maximum value. It's the value beyond which it starts moving. Yeah? So the actual value will always be less than or equal to. It will become equal only at the point of slippage. That's very important, because if you forget this, you will be tempted to use this equation with an equal sign in problem solving, and you will get the wrong answer, because this equation doesn't apply to all situations. It only applies to that point where it is about to. And this thing is so important that there is a name for it. Unfortunately, I couldn't find that name in your textbook, but that is a name you will see, hear in practitioners of friction. So they call it impending motion. Impending motion is the term used to the point where it is about to move. Yeah? So it was preventing motion till that point, and now any slight disturbance and it's about to start slipping. So this is the value. When I say equal, it is the value for the impending motion. Impending motion means that it's just about to move. But other than that, the general relationship is less than or equal. So if we now compare these three coefficients, mu s, mu k, and mu r. One thing is very clear: this is the largest because it's the toughest to start. This value is a little smaller, and this is the smallest of all. Because you can imagine rolling friction. I mean, it has to be small, otherwise you will not see so many wheels there. And one of the reasons it's small is that the contact area is very small. Yeah? So the reason you have rolling friction is not because of the area, because that area is actually nothing. The reason you have rolling friction is the process which I do not want to explain. Yeah? The deformable nature of. So what this also means that if you can guarantee that the wheel will be rigid, although it's not possible to guarantee it in manufacturing. So let's imagine a world where you have a wheel which is completely rigid. Then these are the only two frictions you can have. Because then rolling friction becomes impossible, because rolling friction requires the wheel to be deformable, right? So that's why you can imagine that rolling friction is something you will only see with tires. Do not expect it with solid metallic surfaces. There, the dominant friction will be kinetic friction and so on. Yeah, so I think that's all you need to know. One other thing which is related to this, that now you know that if the tire is trying to rotate in this sense, right? This is the friction, right? And here is another way why this has to be different from these two. Remember, when the tire tries to move, what is this part of the tire trying to do?
Pushing back.
It is trying to push back. So if it were kinetic friction, this friction should have been forward. Do you see the point? In sliding, when you want to slide in a direction, let's say it was sliding. So if it was sliding forward, the friction will be backward. But if it was sliding backward, the friction would have to be forward. But here that's not happening. The wheel is trying to rotate this way, so this part of the tire is trying to go backward, and the friction is still backward. So this cannot be one of these, because we know the rule for that. So it must be a different phenomena, and the phenomena is the tire, not the surface. Right? But this has a consequence. This force is now, the friction force, is now actually I would say an action on the earth, right? So you will have a reaction, right? And that reaction is actually what makes you move. So when you have a rolling tire, the motion of the car is not because of the engine. The engine is only doing this thing. So just like when I jump, I jump not because of my force, but because of the reaction of the earth. My energy was only used for pushing the earth. And the actual jump came not from my force, but from the same is happening here. What the engine is doing is only pushing the earth backward. So the reason you are moving is not because of what the engine is doing, but because what the earth is doing to the car. That is why it is impossible to drive on a frictionless surface. So if you remove all the friction, you will not be able to drive because that mechanism is not there. Then you will need another kind of engine. An engine which can produce a forward force. Like in robots. Remember in robots you have these actuators, and they can produce a spring force. This is not a spring force. So all the cars would be producing spring force if there was no friction between the tire and the road. So you can drive because of friction, not in spite of it. What's that? Yeah, so this is the equation, right? Small f mu r or small f. Small n for normal force, small f for friction force. All the other forces are used, denoted by capital. Capital F net force, capital F applied force, capital F, for example, with a capital G gravitational force, so on and so forth. So here is a list of values of mu s, mu k, and mu r for different materials. Can you see that this description includes both surfaces? Rubber on dry concrete. Why can't we say concrete? Why can't we say rubber alone? Because friction is between two surfaces. So you can never have a friction of one surface. That surface has to get into contact with another surface, and these two combined will determine the value of the friction. So never expect a value for rubber only. Never expect a value for concrete only. It's both. Similarly, rubber on wet concrete, steel on steel, and this also. So this table could be provided to you as a cheat sheet in case there is a problem, because there is no way you can memorize this, right? But it means that when a cheat sheet is provided to you, you are expected to use it. You cannot say, oh, let's assume. Assume आप तब करेंगे जब आपको data नहीं हो available. जब data दिया हुआ है, so it is your responsibility to know that okay, a cheat sheet is available. So there is no room for assuming when a cheat sheet is available to you. This is what you need to remember. So this is now our final model of friction. So regardless of the type of friction, right, we'll always have this diagram, right? So this diagram will have a region where the applied push or pull, because we use push and pull for the applied force, right? Is in a certain range, and the object is at rest because it cannot move, so that will be called static friction. Right? And after that, it will either be kinetic friction or rolling friction, because even rolling friction requires to overcome the static friction. Either there will be no static friction and then this part will be zero, right? Or if there is some, you have to overcome this and only then you can have rolling friction or kinetic friction. And remember that this value has to be small because in this region it has to somehow slide. So some of the bonds are broken, and that's why the new friction is smaller. These two are never the same. Kinetic friction will always be smaller than the static friction, and rolling friction will be way smaller than the kinetic friction. This is something which I already explained. And the next force is the drag force. So drag force now, so it means that now we need another classification. So we have static, we have kinetic, we have rolling. Okay. You can use the same word friction for all the three, and then you can say, okay, dry friction, right? Which is tangential, you can simply call it. You can even use tangential as an adjective, tangential friction. And rolling friction, and then we have drag. So drag is different from all of these because when you look at them, the magnitude is always the same, whether it's rolling friction, kinetic or static. Why is the magnitude always the same? Of course, in this case, the magnitude depends on how far you are towards that point of impending motion, but otherwise it doesn't depend on velocity. So it doesn't matter how fast you are moving. Kinetic friction does not depend on the speed. It only depends on the two surfaces. Got the point? But drag force depends on the speed, because it is a consequence of interaction of a moving body with the fluid. So drag force is only possible when you have a fluid, a gas or a compressible liquid, right? So because it depends on how you interact with it, faster would mean more drag and slower would mean less drag. So the sense in which this force is different from all these three is that the magnitude also depends on the speed. The direction is the same for all of these. All of these four will have the same direction, and the direction is opposite to the motion, right? Or the attempt of motion. In case of static friction, you cannot say opposite to the motion, but opposite to the attempted motion or attempted velocity. So it's the same, but the magnitude of drag force will depend on the speed, right? So that means that if you are actually on a bike, so the faster you move, the more the drag. क्योंकि ये contact नहीं है, ये you are directly coming across those molecules, and so more velocity means more encounter. The frequency of encounter, you hit more molecules per unit time. That's why it increases with velocity. And although we are not going to get into mathematical modeling, but this is a common expression you will see in literature. The force of drag is typically half. There is a coefficient called C, coefficient of drag. Then density of the medium also matters, rho. So denser medium will give you a larger force because the same reason, dense means more molecules per unit volume, so more encounters, makes sense. Then area, right? So the larger the surface, the larger the force. Then speed squared. So this speed squared is typically in the air or gases. If you are very slow, like a truck actually, typically the truck, then it is more likely that the square will actually be just linear. I mean, maybe you will find this equation. but most of the time you will see a square. So cross section, density, drag coefficient, right, and speed. I'm skipping this part. The reason we have this slide is that it tells you where this capital C comes from. So it has many factors, and one of them is the shape. Different shapes will have different. So that's why the rain droplets are spherical, because that gives you the, an optimal value of C, right? Okay, so the value of air resistance compared to rolling friction. So let's say you are driving on a road and you want to know how to compare these two forces. Yeah. Okay. One more thing. Just like I needed a common name for these two, and then a common name for these three. Yeah. So I would also like to have a common name for all of the four. Right. And that will not be friction. That is called resistive force. So now you see that way of organizing your body of knowledge, and there is no way you can forget it if you put these things into a particular order, right? But if you memorize them one by one, then you forget it everything. Right? So air resistance compared to rolling friction. So he's actually giving you 1500 kilogram passenger cars as seen from front, from front matters, yeah? Because it is from the front that you will face the drag force. It is 1.6 meter wide, right, and 1.4 meters high. So these two combined, multiplied together, will give you the area A, right? And you know the mass. Aerodynamic body shaping, we just saw a while ago that the shape determines the value of C. So the shape of the body gives you a drag coefficient of 0.35. So 0.35 is the value of C. At what speed does the magnitude of the drag, which is given by that formula, half C A rho and V squared, right? So V is the unknown here, equal the magnitude of the rolling frictions. That will be mu r times n. So mu r has to come from these two surfaces, for which you have to look at the table, right? Small n will become m times g, because this is not an inclined surface, so just m times g, right? V is the unknown, and we know that the rolling friction does not depend on the speed. So it will simply be mu r times n. So just make these two equal, right? So the next slide shows that. First you draw a free body diagram. So this dot is your car. This is the propulsion, the propelling force, and you have the drag force here. This is the rolling friction, right? They are both resistive forces, rolling friction and drag force, and they are both opposing the force trying to propel the car, and normal force and gravitational force. And you see that for these two, for friction and for normal force, he uses small symbol. This is just a notation. For all the other force, he is using capital. So now we apply the formula. You want to know the speed at which these two forces are equal. And pay attention to this formula. The right side doesn't depend on the speed. So it will always have that value. It means that it doesn't matter whether you move slowly or whether you move fast. You will always face the same rolling friction, because it depends on the two surfaces. It doesn't depend on how fast you move, right? But the left side, which is the drag force, it does depend on the speed. So it means that initially, when the speed is very small, there will be actually nearly zero force. But as you speed up, this force, the drag force, will increase to a point where these two are equal. So you can now compare. So this will give you, before calculation, you can now guess that this will give me the speed beyond which I will have to take the drag force seriously. Before that it was small, so I was ignoring it. Right? So it means this now gives you that that argument which I was just discussing a while ago, that if you are very slow, you can ignore the drag force. Because you have a small value and you take the square of it, remember, square of a small value, if it is less than 1, it is even smaller. Yeah? 0.1 squared is 0.01. So you can easily ignore that. But now, at this point, let's solve this equation. We know everything. We know C, given the question. Rho will be from some table, right? Of the air. You can find this from some table. That table has to be provided to you. It's typically 1. For air, it is 1 kilogram per cubic meter, if I remember correctly. 1 kilogram per cubic meter. Area is also given 2 dimensions. V is the unknown, right? Mu r is from some table, right? And m is given and small g is given. You solve this and you get the value, which is 24 meters per second. So in this situation, 24 meter per second is the speed below which you can safely ignore the drag force. But after that, not. So now you can recall when you are actually moving on a highway, there is a speed beyond which you start feeling the drag force. Have you noticed it? This is because of this. Because till that point, you were only concerned about the rolling friction. But now rolling friction, because this is not changing, right? This has the same value. But this will now keep increasing, so drag will become the dominant force at high speed. And now you can imagine that comment which I made in one of my lectures about reverse swing. Right? Why reverse swing is only possible for fast bowlers. Yeah? Because there is a speed below which there is no such thing as reverse swing. Yeah? So only at high speeds you can imagine this formula to be a dominant force. And this gives actually rise to the new concept which is called the terminal speed. So anything coming from a height, initially it will start with a very small speed, right? So the drag force will be negligible. Imagine a parachute, right? A parachute or any object falling because of gravity. So initially the speed will be small, so the drag force will be negligible. So all the force is that of gravity, right? And what happens? It accelerates because of gravity. The speed gets larger and larger. So what happens? The drag force will also get larger and larger. And there will be a point where these two will become equal. These two will become. So what will happen after that? That is what we mean by. Because after that, the two forces balance, and it can only fall at a constant speed after that. So it will stop accelerating. That's why the parachute works. Why the parachute has to descend at a constant speed? Because of this phenomenon. These two ultimately balance each other. But of course, many people actually expect this equation in the start as well. They argue that okay, if these two speeds, if these two forces are the same, then how is it moving in the first place? No, they were not the same when it started motion. Right? The same is when you are driving on let's say on a highway. When you start driving, at that time there is no drag force. There is only rolling friction, yeah? Or static friction. You overcome that, so you accelerate. When you accelerate, you need a net force. Yeah? So when you accelerate, you are speeding up. The drag force is also building, right? The rolling friction is already there. So there is a point where all these forces will balance each other. But you are already moving. Yeah? So you will keep moving because of inertia. So many people cannot understand this thing, that if the net force on an object is 0 on a highway, how is that object moving in the first place? It was moving, and when it was moving, the forces were not balancing each other. समझ आ गई बात? तो जो equilibrium है वो बाद में आया है, शुरू में equilibrium नहीं था, क्योंकि you cannot start your car in equilibrium, right? You get equilibrium only after a certain point. ये ज़हन में रहे. So, and if you look at this equation, how do you compute terminal speed? If you look at this equation, he actually applied that formula, right? For Fg, you have to write m times g. It's the same thing from the previous example, but applied to a different situation, right? F drag, yeah, half c a rho a v squared. Set these two equal. So this is the point where the drag force becomes numerically equal to the force of gravity, right? And when you solve this equation, you get the terminal speed. This is the terminal speed after which you will have actually equilibrium. Do not confuse this terminal speed with escape velocity, right? That's a different thing. Escape velocity is a separate concept. So how to make sure that the cargo doesn't slide, right? Although you have many examples in the textbook, I would highly encourage you to actually go through those examples one by one and write to me if you can't solve or if you can't understand something. Yeah? We just included one bit of knowledge today. I mean, so far we were only dealing with two things. Equilibrium when the net force is zero, right? And then when there is no equilibrium, which means some net force, and that means you have to apply F equals ma. Today what we did is this. You need to understand this. What we did today has a consequence. And this is what many actually textbooks, many lectures, they miss the whole point. So you write this equation, but to use this equation you need to be very clear about the meaning of each term. So this is clear, yeah? Mass of the particle, yeah, you must have modeled something as a particle, and that has a mass. And A will be the acceleration of that mass or of that particle. The difficult part is this thing. This side, and the reason we call it F net, is that this has to be written as a vector sum of all the forces, and that's why you need a free body diagram, because free body diagram will tell you which forces are there. So it will definitely have some agent like engine or gravity or whatever, or U, right? Then it will have resistive forces, like friction, static friction, kinetic friction, rolling friction, and now you also have drag. So all these different forces are going to be terms on this side. You must do that. Yeah? Only then you can use this equation. So this equation is not for just one or two forces, which you are used to. No. Every force in the free body diagram, that body diagram has to be included here. And drag force you just saw. So each time we learn a new topic, we just add one more term there. Right? And also normal force. Yeah? Normal force, force of gravity. So it means that when you are writing this side, it's better to write this side along each axis. So you will have this side along the x-axis, you have this side along the y-axis, along the z-axis, and so on. Similarly, you will have A along the x-axis, A along the y-axis, A along the z. So now we are asking, this is just one example which is included in this slide. So how to make sure that the cargo doesn't slide? So a 100 kilogram box of dimensions, so the mass is given to you, M. Dimensions are given 50 centimeter plus 50 times 50 centimeter times 50 centimeter, right? Is in the back of a flat bed truck. One thing which is very interesting, these dimensions only matter for drag force. You just saw it a while ago, right? Drag force. Do these dimensions matter for rolling friction? Do they matter for kinetic friction? Do they matter for static friction? No. So sometimes this is just to confuse you. It may turn out that this data has nothing to do with your calculation. Why? Because this box is not moving in the air. It is sliding on a flatbed truck. So it has the sliding friction, the Coulomb friction or tangential friction. And the coefficient of friction only depends on the materials, not on the area of contact, right? So the coefficient of friction between the box and the bed on which the box is actually going to slide is mu s equals 0.4 before motion and mu k 0.2 after motion. And you can see that that value is smaller than this value. And rolling is not possible here. all it can do is slide, right? Now this is happening on the truck, right? But the truck has its own tire, right? So it has to roll. What is the maximum acceleration the truck can have without the box slipping? So you need to look at this diagram now. This is the truck, this is the box, and the whole question is about this box. So you have to model that as a particle, right? And your free body diagram will not be for the truck, but for the box. Right? So now can you now tell me why I have these three forces? I definitely will have normal force, a reaction from the bed, force of gravity by the earth, right? So these forces I can identify. Why the friction force is forward? Because the box will tend to move backward. What makes it move backward? No, because it is at rest, right? When it is at rest and it tries to move backward, it needs a force. Where is that force coming from? Huh? Yeah, so there is no force actually. There is no force, right? It doesn't want to move, right? It has to go with the car. Yeah, so there is no relative motion between the box and the so remember when the truck is moving as a single body, including the box. So that is one body. Yeah. So when you apply F equals ma, you will apply it not just to the truck, but to everything. So it will have to move there. Right? So that is just because of the outside. But that force and that equation is not part of this diagram. Remember, I told you that you will have one free body diagram for each object. The object of study here is the box, not the whole thing. That's why this diagram doesn't have much detail. But if we had this diagram for the whole thing, then we will have F equals ma as well, right? That is not visible. So now this is the only force which you will see, right? And this is now the net force. So now tell me, the force that prevents sliding is actually static friction, and the box must accelerate forward with the truck. So the acceleration of the box must match both in value and in direction to that of the truck. Why? Not because of this diagram, but because this whole thing will move as a single particle. Right? And what is the justification for this equation? Because these two objects, you need some force for them to actually go past each other, right? So because they have to stick together, so they have to move together. Right? इस तरह आप किसी के साथ में बांध दो और वो move करेंगे तो आप दूसरे के साथ move करेंगे, ठीक है? So just together. So what is the question now? What is the maximum acceleration the truck can have without the box slipping? So how do we find that acceleration? Think about it. Any idea? How will acceleration enter this equation? Can you tell me the value of Fs? Can I say Fs will equal mu times n? Mu s times n? Yes or no?
Yes, sir.
But I told you the condition for that. That's the maximum value. How do you know it's the maximum value?
So move to
No, but how do you know that's the maximum value? Yeah, so the point at which it is about to move, right? At that point we can use this equation. So not before. Before that, Fs will just equal the applied force. So now let's try the equilibrium equation, right? What does this equation tell you? This one. Let's start with this one. The sum of all, the vector sum of all the forces along the y-axis has to be 0. Why? Because it is an equilibrium along the y-axis. The two forces have to balance. N has to equal mg, right? N is the normal force, mg is the force of gravity. They have to balance each other. So from this, ay has to be 0. So the acceleration is 0. And now come to that side. What is the net force along the x-axis? Friction force is the only force, right? You saw in the figure there. So that force is, just a while ago I told you how to use this equation. This equation requires the left side to be the net force. What is the net force there? Fs, because that is the only. So why is that the only force? Let's go back to the diagram. Why is that the only force? For that you need to recall the thing to which friction is a response. So friction is a response to what? Either to motion, but there is no motion between these two, right? They move together. So that will be the kinetic friction, right? If it was moving, then you would have kinetic friction as well. Because there is no motion between the box and the bed. So there is only an attempt of motion. Yeah? Because of inertia, it doesn't want to move, so it is attempting to go backward. So it is that attempt of motion which is being prevented by the static friction. So the reason I'm telling all of this is that in your free body diagram, whenever you draw an arrow, you must have an expression for that. Either you must find an agent. So like for this, I know the agent, the earth. I know the agent for this, the bed, right? But for this, I need to know the agent, right? So, and that is the surface which is preventing motion. There is no other force. So it means that when I'm applying this equation along the x-axis, this side will have Fs as the only force. And that will give me the acceleration on the right side. Agreed? Now solve that equation. Fs equals mx. But the problem with Fs is that this Fs, Ax is also unknown here. So you cannot use this equation to solve anything. Okay? So this Fs will have a value between 0, right, and the maximum value. And what is the maximum value? Mu s n. And that is something we can calculate. Right? So do you see the problem? We want the acceleration. The acceleration requires Fs. I cannot use this equation to solve because they are both unknown. But the good news is that he is asking for the acceleration, which is the maximum acceleration, right? So now I can use the maximum force, and for that I can use ms times n. So and N will be mg, right? So now I have all the values. I have the value of G, I have the value of M, I have the value of M US. This will give me the maximum force. That force can be plugged here, and that will give me the maximum acceleration. That's exactly what he has done. But you need to understand that if I change the question, and if I remove this part which requires the point at which it will the maximum, then I cannot use this question. And you will see this thing in the next example. We will not be able to use this equation in the next example because that's a different question. Oh, I think वो example इसमें नहीं, वो book में है. Unfortunately वो book में है. तो वो text book में एक example है इसके बाद. उसमें I would actually ask you to work that out. और वहाँ पे उसने ये ऐसा कुछ नहीं पूछा, ठीक है ना? So then you will realize yourself that you cannot use this equation. You have to use some equation like this actually, वो जो balance equation है. Let me just show you quickly that page. ताकि आपको मैं solve नहीं करना चाहता, मैं सिर्फ आपको बताऊँ जब आप उसको पढ़ेंगे so you need to pay attention to that. Friction. Yeah, ये वाला. So it's this problem, right? So you have the same thread, the same box, the same bit, but this time it is at some angle. Right? And now he's asking you for the maximum value of that angle, beyond which, remember, if you actually increase that angle, there will be a point after which it will start slipping. So that maximum angle requires you to solve one of these equations. And remember, so one of these equations have to be solved to find that value. And he's reminding you that you cannot use Fs equals mu Sn there. Why? Because it has not yet reached there. Right? अच्छा, जो next three chapters है, chapter 3, and Fakhar, you have to think about this. How do we actually reduce these slides? There are 3 documents, but we will only pick certain very small number of topics from them, because we need to finish them in one lecture, right? So we need to somehow remove many slides from these 3 files, right? And most of the things you already know, because I discussed this in one lecture. So I'm skipping most of these questions right now. Okay, so now you know what energy means. What was the definition? It was not a definition, but it was something close to a definition, which I told you about energy. So how will you, I will not say define, because define is a very strict word. For example, what do we mean when we say this? Let's say I have this object, right? And I say, what do I mean when I say that this object has energy 10 joules? What does that mean? So energy is actually the capacity or ability or whatever name you use. And because none of these is a precise word, that is why whatever I say will not qualify for a definition, because definition has to be strict, right? Now that doesn't mean that you see definition in textbooks and you say, oh, I saw a definition. Anyone who tries to define energy doesn't know what a definition actually means. Right? There is no definition of energy. You can only develop a sense for what it is. Yeah? So don't try to define energy, but let's say indirectly, right? I told you Newton did not try to define force. What he said, he gave you the first law, and from the first law, you have a sense of what we mean when we say force. But he never gave a definition of force. Right? So the same is what we are doing. So when I say that this bottle has an energy of 10 joules, it means that this bottle, because of that energy, can bring some changes in this world. And that change could be trying to move something, or trying to lift something, there are three types of changes you can imagine. You can either make something move, right? This way or this way, right? Or you can actually change the type of substance. Remember, in chemistry, what do? In chemistry, when there is a reaction, nothing is moving, everything is in that beaker, yeah? But what is happening? The type of substance changes. Sodium and chlorine, you combine them, it becomes sodium chloride. The sodium chloride has different properties from both sodium and chlorine. So you have changed the world by changing the type of substance. So you can either, or you can change the shape of something. I can do that. Like I have these pages, and what am I doing? It is still there. It is not moving, but I have changed the shape. So bringing a change in this world could either mean a change of shape, a change of type of substance, or motion as a whole. So this is, I gave you too many things, but none of them qualifies as a definition. But you still got an idea of what we mean when we say that an object has energy. One more thing, the energy has to belong to this object. This is very important. I say energy of this. So it is a property, energy is a property of the thing. So you can use all of these. Ability to make things happen, associated with heat, electricity, things like that. And I actually ignored one thing, thermal energy. Thermal energy can also, it can also make things move, for example, right? Like what the engine is doing. It is making those gases expand. Yeah. So expansion can be seen as a change of shape, right? Expansion. So what you need to understand is that more important is not to define energy, but to know this law of conservation of energy. Whatever energy is, one thing is clear, that in a system which is not interacting with anything else, right? If it is an isolated system, no interaction. Why do I say isolated system? Because when it is interacting, it is possible that something can happen from outside. So if I actually disallow all of those interactions, everything inside this system, I can have energy convert from one form to another, right? But the total energy cannot change. That is what the law of conservation of energy is about. So now you know kinetic energy, it's the energy of motion, right? And potential energy, it is associated. Beta ek class mein na kare baat. So kinetic energy is the energy of motion of the entire thing. So even if you are talking about this whole planet Earth, because it is moving as a whole body, it will have kinetic energy. Remember. So if you are talking about a car, for example, in that car you have the driver, the seat, the engine, everything. So kinetic energy is a term you use when the body is moving as a whole. Yeah? So which means that any motion inside the body which does not contribute to motion as a whole will not count as kinetic energy. You got something? Yeah, nahi. So let's think about this. I will now have a hypothetical situation, right? Let's say this is some system, either a car or a planet or anything. And let's say there I have these three bodies. So particles inside the system. But I want to call this as my system, or as a particle, as one particle. So now if these objects are moving, but this whole object is not moving, this has a kinetic energy, this has a kinetic energy, this has a kinetic energy. But this system has no kinetic energy. So the kinetic energy of a system depends on your definition of the system. So if you define a system, so inside a car, a driver can be actually jumping like that, but the whole car will have zero kinetic energy if the car is not moving. This is what you need to understand. Right? So, what do you mean by potential energy? Potential energy is when you have a system, right? And there are interactions within the system. And those interactions are only associated with the position. So not with the motion. It is not because of the motion. So let's think of it. So think of Earth and you as one object. This is what I'm trying to do, right? Let's say this is you and this is Earth. So if I think of these two as a single object, so you falling down, right, or you going up, all of this is happening inside the system, right? So this will contribute to what we mean by potential energy. Why can I call it potential energy? Let's say you were here and you moved there. So what has changed? Let's say you were here at time 0, right? And at time t1 you are there. So what happened between time 0 and time 1? Previously there was a smaller distance between you. At a later time there is a... Now you see why position is important. Yeah? Because of the position. Yeah? So now what has this... I told you energy is the ability to change things. So what has this distance given, which ability has this distance given to both these objects? They can now come closer again, right? This will not go, but this can come back. But remember, this ability is not because of this alone, it is because of this and this together. Why? Because Newton's law of gravity is capital G, M1, M2 divided by R squared. So whenever you speak of potential energy, you must remember that it is the energy of interactions within the system. So I can call it potential energy. Why? Because both the object and the Earth are part of the same system, and because I have separated them, they can now come back. The same I can say between a proton and electron. Yeah? Let's say a proton and electron are here, so they have zero potential energy. But if I separate them, now they have some potential energy. Why? Because they can come back. But it doesn't mean that I say that this proton has a potential energy and this electron has. That is wrong. Why? Because potential energy is the energy of interaction, and interaction always requires two bodies, at least two bodies, sometimes more. So now if I ask you, what is the potential energy of this object? What will be your response? This is the mistake which we typically make. Yeah? If this height is h, the mass here is m, and the mass here is capital M. So you will see it everywhere that mgh is the potential energy of. That is wrong. What actually the correct version is, the potential energy of the system which has the object and the Earth together, right? That is to which you can call potential energy. So now the question is, if this is not potential energy, what is this? Let's change the system, right? So now I change the system, and if I leave it, what will happen? It will fall, right? And I cannot call it potential energy. So what will I call it? Kinetic energy तो बाद में बनी है ना? So what made it? Which energy converted to kinetic energy if it is not potential energy? Energy तो इसमें नहीं थी ना? You have to start from scratch, yeah? initially I had this whole thing as an object. So I could call it potential energy. That's something you know, energy is in. But now this is my object. So I raise this object from here to here. So in that time, this object was interacting with me. I was the agent. So this is work. This is the difference between work and energy. Right? Work is the term you must use, although you will still have units of energy. You will still call it 10 joules or 5 joules. But you have to call it work when it is a result of an interaction with the outside world. पहले मैं इसको work क्यों नहीं कह रहा था? Because it was the same system. I was also part of the system. Yeah. So work is a term you only use when things are happening at the boundary between a system and the surrounding. But if you make the surrounding part of the system, you cannot call it work. ये बात समझ आ रही है? It's the same as heat. Remember, let's say this air conditioning system is working as a heater, right? So, and this is heating this room. You can only use the word heat if this AC is outside the system. So think of the room as one system and this heater as something which is part of the surrounding. Then you can call it heat. But now change the system. Let's say I have a new system which includes the heater. Now you cannot use the word heat anymore. Then you can only use one word, and that is thermal energy. So this is what you need to understand. Yeah? Potential energy, thermal energy, kinetic energy, these are names which you use for systems. Work and heat are names you can only use for interaction. There is no heat of a system. So you cannot say this heater has a heat of 10 joules. You can't say that. Yes?
How do you define which thing is part of the system?
You define the system yourself. So when I am interested in this object only, that is my system. Remember, what were you doing in a free body diagram? You have a body and you have an imaginary boundary, right? That was a hypothetical boundary. It was not a real boundary. So that was actually your declaration that this is my system. You can have one electron as your system. It's your choice. Yes?
सर पोटेंशियल एनर्जी mgh है तो वो मास किसका होगा, अर्थ का या फिर इंसान का इस फॉर्मूला में?
So when you say that mgh is the potential energy, so m has to be from the object, right? So आप ये समझेंगे कि इसका मास कहाँ गया? वो small g में है, small g की कैलकुलेशन आप देखिए. Do you remember how you calculate small g? We calculate it from the Newton's law of gravity. Capital G, m1, m2 divided by r squared equals mg. So m cancels and small g depends on this mass. तो उस g में already उसका mass शामिल है. अब just look at the formula. This formula has 3 variables. This m belongs to that object. This g belongs to this object, right? It doesn't belong to that object. And this h belongs to both. H is a separation between the two objects. So मैं कैसे कह सकता हूँ कि ये इसकी energy है? It is stupid to say that. Half mv squared के बारे में मैं गलती नहीं कर रहा. क्यों? Half mv squared में half mathematics का है, m object का है और v भी object का है. So I can easily say half mv squared is the kinetic energy of that object. But this I cannot call it the energy of that object. For that I need to define a system which has both. Yes?
Say, I suppose engage one in the question. That
Yeah.
the question will define the system, right?
Yeah, the question will be asking you something, and maybe one question is solved by two students in a totally different way. You define, but this is what I'm telling you, that when you define this as your system, this mgh will still be in your formulas, but you will not call it potential energy. You will have a different name for it. And what is that name? I told you. Work. Why? Because this mg now What is this mg? It is the force. And that force is multiplying the displacement. And force times displacement is work. So when you call it work and when you call it potential energy, it depends on how you define it. The formula cannot tell you whether it is work or potential energy. ये एग्जाम्पल मैं इधर दे चुका हूँ ना, इसको आप हीट कब कहेंगे और इसका आप थर्मल एनर्जी कब कहेंगे, ये आपके ऊपर डिपेंड करता है. ठीक है? Is there any other question? Okay, thermal energy I'm skipping. So this diagram is very important. In order to consistently use these two terms like work, energy, right? Kinetic energy, potential energy. So you define your system, right? And it's up to you. Then everything inside the system, you will use the word energy, and that energy will have different forms. So sometimes it will be in the form of kinetic energy, sometimes it will be in the form of, sometimes thermal, sometimes chemical. One thing about thermal energy needs explanation, right? So when you think about thermal energy, you have molecules, yeah, atoms, they're bumping into each other, bonds changing. So you can say, why am I not calling it kinetic energy? Why am I calling it thermal energy? Yes? Yeah, so you know, when you say kinetic energy, you need to be clear about the system. So if that atom is your system, then you can call it kinetic energy. But now you are talking about this larger system. And is this larger system moving as a whole? No. You cannot call it kinetic energy. You will only call it kinetic energy if this whole thing moves. So it becomes thermal energy. Yeah, the name changes depending on your definition, right? So potential energy, kinetic energy, thermal energy, chemical energy. Chemical energy is the term you use when changes of substances are involved, right? If no substance changes, then you cannot have chemical energy. But what is important is that all these names are types of energies, and that is a term which you can only use inside the system. Now come to the environment or surrounding, right? And remember, it is up to you whether you call it the environment. You can bring everything into one system. That is when you use the word isolated system. So if you make the entire universe as a single system, that is isolated, yeah? Right. So now, the system can interact with the environment by two different mechanisms. One mechanism, so it means that what we call work and heat, they're actually processes of interaction. They still have units of energy, but we never call them energy, right? So one process is called work and one process is called heat. Work is the term you use when forces are involved. So whenever there are forces, electrical forces, gravitational forces, yeah, mechanical forces, so all these forces interact, and the work and you attach work to forces. Why? Because it's organized. Heat is the process you use when it is disorganized, when it is random. So when the energy is coming from the surrounding to the system in a random fashion, you call it heat. Yeah? Because it is so random, yeah? My molecules, atoms bumping, you cannot trace them. But if you can trace them, so electrical energy, it will be part of work because it's organized. Yeah? But heat is the thermal energy. I think that's, and one more thing, don't think that you can have work and heat only coming from the surrounding to the system. It is also possible for the energy to leave the system in the form of work. So the system can expand to work on the surrounding, right? If the environment is pushing the system and it actually compresses, it will do work by the surrounding. But if the system, so like, remember the gases in your car, they have to expand and they make the parts of your car move. So if you define that gas as your system, it is working on the surrounding. Yeah? And if it is hotter than the surrounding, yeah, so it can heat the surrounding. So which you will call this cooling and you will call this heating. But for the math, it's still heat. Yeah? Heat in, heat out. Work in, work out. So if you understand all of these things, the rest I think you will, I will highly encourage you to read. But there is one thing which is very, very important. These resistive forces like friction, drag, they have a special feature which no other forces have. They will always reduce the kinetic energy. So if you think about other forces like I apply a force, gravity applying the force, yeah? Electric forces, magnetic forces, they can actually increase the kinetic energy. If you have a smaller kinetic energy, they can increase it. If you're already moving and they come in your opposition, they can decrease it. But when they stop you, they can then increase it in the other direction, right? So let's say I'm moving and somebody comes to stop me. He will first bring me to a stop and then he can increase my kinetic energy in the other direction. This is not possible for resistive forces. Why? Because they stop, they can only decrease your kinetic energy. They will never be able to increase your. Why? Because they always are opposite. So remember, when you compute work, work is the integral of force and displacement, right? So positive work means energy enter the system. Negative work means energy. Now, how do we know whether it's positive or negative? So if the force and displacement are in the same direction, you have positive work. So whether I'm going this way or if I'm going this way, in both cases, if the force and displacement are the same, in the same direction, work will be positive. It doesn't matter whether I move this way or this way. Why? Because work is done on me. But that is not possible for resistive forces. Why? Because resistive force will always be opposing me. So that dot product will always be negative. So now that brings us into a system, to a new equation. The equation is this. Work external, EXT, external work done on the system. When I say work, it will always mean work done on the system, right? In this course. In some courses of thermodynamics, the convention can change. So it means that if the work is done by the system, then this will become negative. So the sign will automatically determine. You don't need to write it yourself. So work done on the system will increase the kinetic energy of the system. This is a rule which you need to remember. Work done externally. But if it is positive, if it is negative, it will decrease. So it means that the work by resistive forces will always be negative and they will always decrease the kinetic energy. This is what you need to remember. So I'm just quickly showing you a few equations. Half mv squared kinetic energy, right? This equation, the change in kinetic energy, remember, of a system. Kinetic energy is not something you can attach to the boundary between the system and the boundary. So final kinetic energy minus initial kinetic energy will equal the amount of work done by an external force. This equation is only valid when you assume only one type of interaction, the work interaction. So if it happens that there is also thermal interaction, then this equation is wrong. Right? So you need to be clear when you can use an equation. This equation assumes that work is the only type of interaction. And this is the reason which I already explained. So sign of work, so work will be positive when it is done on the system, negative when it is done by the system. Okay, I think. So आप quickly मुझे बताएं, if you are raising a body above the earth to a height, right, and that object is the system, Is this work done on the system or is it work done by the system?
On the system.
Why?
Resistive forces.
No, the reason आप गलत बता रहे हैं
सिस्टम का वर्क क्या नहीं
वर्क जो फोर्स है वो और डिस्प्लेसमेंट दोनों इन लाइन है ठीक है नाउ टेल मी let that object drop now. Is this work done by the system or on the system? No, it is still on the system because now it's gravity. This is a very common misconception. You know आप क्यों गलत कर रहे हैं क्योंकि आप सिस्टम गलत डिफाइन कर रहे हैं ना मैं आपको कह रहा हूँ दिस इज एन ऑब्जेक्ट and I am raising it above the ground. I am raising it. So this is my force. And this force must balance gravity. जिसका मतलब ये वो net force है. I must have balanced the gravitational force and this must be and on top of that. Right? And now I raise it to that point. The displacement is also upward and the force is also upward. So this is work done on the system by me and I am part of the surrounding. Right? Now, that object is now dropping down. This force is not the force by the object. It is the force by the gravity. And it is still coming down. So, in both these cases, it is work done. So, अब मसला ये है कि हम फिर क्यों कहते हैं कि ये वर्क डन अगेंस्ट है क्योंकि यहाँ पे हम सिस्टम गलत डिफाइन कर रहे हैं ठीक है अगर मैं इसको सिस्टम डिफाइन करूँ अर्थ और इसको तो इस केस में एक्चुअली अब अनफॉर्चुनेटली इस चैप्टर में मैं उस इक्वेशन में जाना नहीं चाहता बट टू समराइज दिस आई एम एक्चुअली इंक्रीजिंग पोटेंशियल एनर्जी And in this case, if you define this as your system, so if you define this as your system, it is losing kinetic energy. And here, sorry, it is gaining kinetic energy. And here it is losing kinetic energy if you have initial. So because of those two, you have to bring in potential energy into this equation. Right? Potential energy के लिए हमें अगले चैप्टर में जाना पड़ेगा इसलिए मैं यहाँ पे इसको लूँगा So मैं असल में उस चैप्टर में that chapter was limited to the equation between external work by the system or on the system and the change in kinetic energy, right? The next chapter is about potential energy. तो इसलिए ये discussion थोड़ी सी complicated हो गई. Now I'm quickly going to those parts which explain the potential energy. Yeah. Okay, so now this is the important part, right? This is something which I explained in a very crude way. This is more organized. So let's say you have two objects, A and B, right? And if you model them separately, so this is one object, one system, this is another system. Any interaction they can have with each other will be, you will use the word forces, A on B, B on A, and anything that happens to the system will qualify as work. Work done on the system, work done by the system. But if you now make a new system and bring A and B into the same system, then all these interactions are within the system. Here you were calling it work. Forces works. Now you will call it potential energy. So the whole level changes. So now you can see the. Now this is the reason. System 2 includes the interaction within the system, right? Since external work is now 0, remember external work is 0 because the boundary is now inside the system. There is no boundary. We must define an energy associated with the interaction within, and that is called the potential. This is now the definition of potential energy. Potential energy is the energy of interaction within the system, not with the surrounding. So this means that the energy of interaction with the surrounding will be either called work or heat. So now you look at this equation. Delta U is the change in internal energy. This is now the work done. Now this work is internal work. Right? Work done on A, work done on B. Why do we have a negative sign here? Where does this negative sign come from? बाई 3 यानी सराउंडिंग के साथ इंटरेक्ट नहीं कर रहा. Basically यहाँ पे ये हो रहा है कि total the change, क्योंकि everything is happening within the system, so the total change in energy has to be zero, right? And now it has two terms. One is delta U, and one is these two terms, these two works. Delta A, WA plus. So everything has to add up to zero. So WA, WB, delta U. Because of this equation, when you leave delta U on this side, these two will go to the other side. So this negative is a consequence of your new definition of the system. ये by the system, on the system की क्या खत्म हो गया. Okay, now everything is in the center. So अब आप देखें कि इसने वो जो example में बता रहा था. This is the earth. This is the object, right? So the change in now so let's say this drops. Yeah? The object drops from a height of some height back to the ground. So look, the force of gravity on the object is mg, and because you have y upwards, so it's minus mg, right? Then that multiplies delta y, and this is now the change in potential energy. But remember, he's calling the change in potential energy, and he's attaching it to g, which is the whole. So we can now define a new quantity, which is the gravitational potential energy mgy, and we'll attach it to the. Actually, you can attach it to the gravitational field. The reason he is using capital G here is that instead of talking about this object and this object, why not talk about the gravitational field between the two? This is a more reasonable description. Compare it to two plates of a capacitor, right? You have one plate of a capacitor, another plate of a capacitor. You say this is positively charged, this is negatively charged. The whole capacitor is neutral. Why? Because positive and negative cancel out. So actually there is no charge. But what has happened? The positive and the negative have been separated. And this separation is internal to the system. Right? Because you are talking about the capacitor as one. So this is internal interaction. So this will be potential energy. And that potential energy will be stored not on the plates but between the plates. So if you're now asking that mgy, which you call the potential energy, where is it stored? It is not stored here. It is not stored in the earth. It is stored in the space between the object and the earth. Remember this thing. And that is why when it drops and when they touch each other, there is no space left, no potential energy. So potential energy is stored in the space, not in the object. And this is now the third. So to recap, this lecture is primarily about three types of three aspects of interactions. One is actually work interaction. Although we discussed thermal interaction, heat, but this is not part of the course. So you can ignore any discussion related to thermal energy. Yeah? That was only to make things into the context. So you should only be concerned with work interaction. Work done by the system, work done on the system. Then the change because of that interaction. So what change can you bring within the system? A change in kinetic energy or a change in, now you want to say, potential energy. if you have a system with two objects within, they can interact, and that interaction is what you will call potential energy. But can you imagine how you can change that potential energy from the outside? Can you do that? So remember, work interaction from the outside. Imagine there is someone outside the earth, right? Or let's say I make myself outside this system. So I declare myself as, क्योंकि ये hypothetical boundary है ना? So I define the object, the earth, and let's think of myself as part of the surroundings. So I'm neither part of this object nor part of the earth. So when I'm actually bringing this object and I'm changing the height, this is now work done on this whole system from the surrounding. So what does it mean? That the external work can change. If I'm making this at constant velocity, the kinetic energy will not be changing, right? The kinetic energy will only change if it is accelerating. So if I'm raising an object at a constant velocity, all I can do is to increase the potential energy of this system. But I'm outside the system. So what does it mean? That W can give me not only a change in kinetic energy, but also a change in. So my new equation will be this. W external, you can now write a new equation. KE of the system plus PM. Assuming that you only have one type of interaction, and that is the work interaction. Thermal interaction must be 0. So it also means that if you include thermal interaction here, right, something related to thermal interaction, then you can also increase thermal energy. So if you want a single equation, on the boundary you will have work interaction plus heat, right? Work plus heat. Change in potential energy, change in kinetic energy, change in thermal energy. But in this course we are not considering these two. We are only concerned with work interaction and work interaction and giving rise to a change in kinetic energy, a change in potential energy. If the work interaction is 0, then all you can see is a conversion between kinetic energy and potential. That is what happens when you drop something. When you drop something, there is nothing external. Kinetic energy has to convert into potential energy. So everything is done within the system. Now, this way of looking at things. Remember, in one of my lectures, I wrote 2 equations. And I think you can also see them in notes, right? So I said that if I start with force, and if I integrate the force over displacement, right, by taking the dot product, I get a thing, because everything in this term is happening at the boundary, right? Force can only exist as an interaction at the boundary. You cannot have a force within, right? So this is called work, and this will give you a change in, now you can say, kinetic energy or a change in potential energy. So this is basically, this was chapter, I would say, 9, and this was chapter 10. Now in chapter 11 we change this side. Instead of integrating the force over displacement, and the argument is that force cannot do anything unless it is allowed to change the boundary. If you restrict the force to one point and you don't allow it to change the boundary, to push the boundary or pull the boundary, it cannot bring any change in the world. That's why this integral is important. So अगर मैं इसको zero कर दूँ, so then force cannot do anything, right? So that's why the actual action is done by the work, not by the force. समझ में आया? So here I'm now changing my perspective. Instead of looking at things in space, let me look at things in time. So just like nothing can be done in zero space, nothing can be done in zero time. So it means that for real action, I have to integrate the force with respect to time. And that will give me impulse. So impulse is another language associated with the interaction. Work is one language of associated with the interaction, but I cannot say impulse plus work. Why? They are both interactions, right? Why can't I say work? जिस तरह मैं आप कह रहा हूँ work plus heat. I cannot say work plus impulse. Why? Because they have different units. यहाँ पे force time के साथ मल्टीप्लाई हो रहा है, यहाँ पे force displacement. So this will be a separate perspective. I am not allowed to mix these two perspectives. There I could do it because heat was also a form of energy, work was also a form of energy, kinetic energy. So there everything actually matched. But here I can have my new chapter, but I am not allowed to mix these two in an equation. But what I can do here is that this will give me a change of something else, and that's something you already know. A change in. I discussed this in one lecture, and you can also find it in the notes. You can derive this from Newton's law. F equals ma, right? And ma is m dv by dt, right? Bring that dt to this side. So there you have m dv. And mdv is change in momentum. So the impulse, when you use impulse as the quantity mathematically representing the interaction, so now you can say that I can mathematically represent the interaction either in the form of work or in the form of impulse. In the form of work, it will give me a change in the kinetic energy or a change in the potential energy. But when I model that, so it depends on the language I am using. In this language, it will give me a change in momentum. One thing is very important. Momentum is a quantity you can attach to a system. So momentum of a system. But you cannot say impulse of a system. Impulse is only defined for the boundary. Yeah? Interaction between the system and the surrounding. तो हमारे पास ये लिस्ट आ गई कि heat, work, impulse. They are quantities only. They are actually processes. Yeah? At the boundary. Momentum, kinetic energy, potential energy, thermal energy, chemical energy, nuclear energy. They are all quantities attached to the system. Okay? So why do we care about this law? Why do we care about this equation? वहाँ पे हमने एक चीज डिस्कवर की है ना कि if the external work is zero and if the heat interaction is also zero, I can say that the total energy is zero. So law of conservation of energy actually comes from this equation. I define a system with no boundary. Yeah. So no isolated system. Even if it is a boundary outside, there is nothing. So law of conservation of energy is a consequence of this equation. Law of conservation of momentum is a consequence of this equation. Why? If I imagine a system which is not interacting with the external world, so then this force will be zero, right? The net force. Imagine a system defined in such a way that there is no interaction with the boundary because it is so large that there is nothing outside to interact with. So everything inside the system will have this term equal to zero, right? So what can happen? Inside the system, in one part of the system, the momentum can go up, and the other part of the system, the momentum can go down. So the law of conservation of momentum is a consequence of this equation. So you don't need to actually assume those laws, that you can derive those laws from these two equations. But there will be some problems for which this will make sense. The good news is that in this law, if you know that there is thermal interaction, right, and you are ignoring it, this equation will give you the wrong results, right? Because you know something is there and you are ignoring it. तो बात समझ आए? इसकी मिसाल ऐसी है कि मैं कोई गन फायर करता हूँ ना, so you know in gunfire you cannot ignore thermal energy, right? Because there is fuel involved, yeah? There is explosive involved, so you cannot say that there is only work interaction. There is also. So if you use this equation for gunfire, chances are high that you get the wrong conclusion. But here, in this equation, you are not even looking at that side. This is a completely different side. So this law will still work for the gunfire. Because in time, this is the only thing that is happening. And you cannot say, oh, why did you ignore those? Because this is not energy anyway. ये बात समझ आएगी? तो कुछ प्रॉब्लम्स में लॉ ऑफ कंजर्वेशन ऑफ मोमेंटम आपको ठीक रिजल्ट देगा, और जो ये कॉम्प्लिकेटेड लॉ है आपको गलत रिजल्ट देगा. अभी हम क्वेश्चन